gases that exist in the nature are real gases. The real gases try to show ideal property at certain conditions. The real gases show the deviation from their ideal gas behavior because of the conditions. As you know that in the previous class, we're talking about the gas which follow this law or which follow this ideal gas equation PV equal to nRT. No doubt that is ideal gas, we say. Means whenever the gas obey the law PV equal to nRT, it is said to be ideal gas. But the difficulty arises when we try to test how far this relation PV equal to nRT reproduce the actual relationship, pressure, volume, temperature of the gases. If PV equal to the PV not equal to nRT, PV is equal to not equal to nRT, then it is said to be real gas. To test this point, pressure, volume, temperature relationship, if you plot the graph between the product of pressure, volume versus the pressure, the plot of gases at constant temperature will get PV will be the constant. The PV versus P graph at all pressures will be straight line to the x-axis. It can be seen easily that at constant temperature PV versus P plot for the real gas is not a straight line. So the graph PV versus P for the real gases is not a straight line. There is a significant deviation from ideal behavior. Look at this graph where the product of pressure volume is taken on this y-axis. Here is the y-axis. Here is the x-axis. On x-axis, what is taken? Pressure is taken on x-axis. When pressure increases, see, the pressure is increasing in this line on this x-axis. Pressure increases from 0 to 1, 2, 3. The product of pressure and volume is increasing on y-axis. If it is ideal gas, we can get a straight line to the x-axis. If it is ideal gas, we'll get the straight line which is parallel to this x-axis. But most of the gases are real gases. But it is very difficult to maintain the conditions to get ideal gas. And look at this, there is a hydrogen, there is a helium. The gases are showing that straight line above this ideal gas. They are showing the positive deviation they are showing hydrogen and helium above this horizontal line, straight line. Look at this carbon monoxide and the methane. When increasing of the pressure, the graph is, the PV is decreasing, the product of pressure and volume is decreasing in this line. When increasing pressure, again it increases. At one particular pressure, it will be meeting this ideal gas line, intercepting at ideal gas line. Similarly, for the carbon monoxide also, carbon monoxide, intercepting at one particular pressure. That means, so at certain conditions of temperature and pressure, real gases will become the ideal gases. Real gases will become ideal gases at certain conditions. So that means from this graph, PV versus pressure, from this graph, so we get the two types of lines, positive deviated lines and the negative deviated lines we get from this graph. And also, if you plot the graph between the pressure versus the volume, the pressure versus the volume, if you plot the graph, then for the ideal gas will get the curve, at given constant temperature. If the temperature is constant, at the constant temperature we can get the line, the pressure versus the volume as per the Boyle's law. When pressure increases, the volume decreases. When the pressure increases, here the pressure increasing sign. When the pressure increases, the volume decreases. The volume decreases. For example, at high pressure, the volume of the gas here, at low pressure, the volume of the gas is here. That means the pressure difference, so the different volume means at high pressure the volume will be compressed of the gas at the given constant temperature. And now you can see for the ideal gas there is a curve you can see, and for the real gases also the same curve we see, but both real gases and ideal gas meeting at one point, intercepting. That means real gases will become ideal gases at low pressure. At low pressure, here is the low pressure we say. Low pressure. And at high pressure, the volume is more for the real gases. That means high temperature and low pressure, the real gases would become ideal gases. Here, what we understand from this, deviation from the ideal behavior also becomes apparent when pressure versus the volume plot is drawn. The pressure versus volume, the plot of experimental data, real gas, and that of theoretical calculated from the Boyle's law should coincide. It is apparent that at very high pressure, the measured volume is more than the calculated at low pressure. The measured and the calculated volume approach each other. So, already we discussed about this graph. And from the two graphs, what we understand is that why do gases, from the two graphs, what we understand, why do gases deviate from the ideal behavior? What could be the reason? What are the conditions under which the gases deviate from ideality? So we should learn what conditions. We find that two assumptions of kinetic theory do not hold good. In earlier class, I was discussing about kinetic theory of molecular gases, kinetic theory of molecular gases. So, if you focus on two things, we'll understand there is no force of attraction between the molecules of a gas. This was one of the assumptions. As per the kinetic molecular theory of gases, what kinetic molecular theory says? There is no force of attraction between the molecules of a gas. The second point, the volume of the molecule of gas negligibly small in comparison to the space occupied by the gas. If the first statement assumption is correct, Really, there is no force of attraction between the molecules of gas. Simple, the gas will never be liquefy. However, we know that the gases do liquefy when we cool and compress it. Liquids are formed very difficult to compress. Once the liquid is formed, very difficult to compress. This means that the force of repulsion are powerful enough and prevent the squashing of the molecules in a tiny volume. If assumption B is correct, the volume of the molecule of a gas is negligibly small in comparison to the space occupied by the gas. If this assumption is true, the pressure versus volume graph, experimental data, and the theoretical calculated from the Boyle's law should coincide. The real gases show deviation from ideal gas law because the molecules interact with each other at high pressure. The molecules of gas are very close to each other. The molecular interactions start operating at high pressure. Molecules do not strike the walls of the container because these are dragged back by other molecules due to molecular attractive forces. This affect the pressure exerted by this affect the pressure exerted. This affect the pressure exerted by the molecules of the walls of the container. Thus, the pressure exerted by the gas lower than the pressure exerted by the ideal gas. The repulsive forces also become significant. The repulsive interactions are short-range interactions. Short-range interactions are significant. The repulsive forces are also significant. Repulsive interactions are short-range interactions and are significant. Volume of the molecules are almost in contact. This is the situation at high pressure. The repulsive forces cause the molecules to behave as a small but impenetrable spheres.